lovely introduction. I am Katerina, I am a data scientist at NVIDIA, and I like everything related to AI. And today I'd like to talk about a relatively new and very exciting direction of AI, which is geometric or graph neural networks learning. I'm going to teach you today on the fundamentals of graph neural network training, and I'll also show you a couple of examples of use cases where you can apply graph neural networks. But before we start, just out of curiosity, please raise your hands who already have experience with AI and deep learning in general. Oh, good, good. For those of you who have not raised your hands, no need to worry. This talk is fundamental, and I really hope you will also understand the basics from it. All right, let's dive in. So those of you who already have experience with AI and convolutional neural networks, you know that those are particularly good when dealing with structured data. By structured data, we understand the data which lies, for example, along a temporal axis or on the Euclidean domain in the form of 1D signals, speech, or text, or in 2D images. In case of 3D, it's volumes. But there is so much data in the world which is unstructured, and graphs are particularly useful in order to describe this kind of data. So let's take a look at a couple of examples of unstructured data. For example, 3D volumes. In volumes, in contrast to images, when we have pixels, we have vertices. So this data, like volumetric meshes or surface meshes, they are represented by vertices. And such vertices can have arbitrary number of connected vertices, and these connections can be also differently weighted. So it's definitely a messier environment to work on compared to structured domain. Another example of unstructured data are social neural networks or recommender systems, and also knowledge graphs representing relationships between different objects. So you may also wonder, can we apply graphs on structured data? And as you may have guessed, the answer is yes. And for example, an image is also a graph on itself. So it's a special kind of a graph called grid graph, where we represent the pixels as nodes in the graphs, and they are connected by imaginary edges. Important to say here, though, that it's a little bit impractical to use images as graphs, because if you have big images, it means that such graphs will be huge, and this might be computationally inefficient. So, in a nutshell, you can basically model anything as a graph. And if you can model something as a graph, and then you have enough data, you can apply deep learning to it in order to derive some new insights from this data. But before we start with the basics of training and learning, let's revisit some basics of graph theory. And let's consider these bright dots as our nodes in the graph. Nodes in the graph represent some items or entities of the real world, and we also can represent the relationships between these nodes, between these items, and these relationships on the graphs. They can be reflected by edges. And such edges can be directed and undirected. So based on the direction of edges, we can classify our graphs as directed and undirected. In an undirected graph, we have symmetrical relationships between entities, and usually these relationships are mutual. So one example of such undirected graph is the social network Facebook, where we have friendships between users, and these friendships are considered to be mutual, at least on the technical side. The networks like Twitter and Instagram are examples of a directed graph. So in these networks, users, they follow each other, and such following does not necessarily have to be mutual. So Twitter and Instagram are examples of a directed graph. In undirected graphs, we have the notion of degree, node degree, and node degree is basically the number of edges associated with a given node. When we have a directed graph, we extend it further to the notion of in degree, the number of incoming edges, and out degree, the number of edges which are leaving the node. Graphs can be also homogeneous and heterogeneous. So homogeneous graph is the graph where we have entities of the same type, like all our nodes are of the same type, and all of our edges are also of the same type. So again, Facebook is an example of a homogeneous graph. There are also heterogeneous graphs. In heterogeneous graphs, we have entities of different types. And also relationships between these entities is also of different types. So it's a bit messier compared to social networks. So one good example of such a heterogeneous graph is an e-commerce platform, where we have users and we have products the users can either view, put to the basket, or buy. So these are different relationships and different actions the user can do. And this can be all reflected on a single graph. And this graph can be used for further training. Another important notion applied to graph is the notion of neighborhood. By the notion of neighborhood, we understand, so we have our node A, and if we take all the adjacent nodes, this is the neighborhood of the node A. And we call it one-hop neighborhood for all directed connections. If we want to extend it further and take the neighbors of the neighbors and include them also in this neighborhood, we call it the two-hop neighborhood. And it can go even deeper and deeper until like k-neighborhoods, right? You may also wonder what kind of data structure we can use in order to represent our data in order for our computer to understand our graphs. And one good representation is a matrix representation. An example of such a matrix representation could be an adjacency matrix. In adjacency matrix, we encode the values of connections between nodes. So if we have an edge between node A and B, the matrix cell A and B, with the indexes A and B, we put the value of 1. Note that for undirected graphs, this matrix is symmetric. It's a symmetrical matrix. And if we have, for example, weighted edges, we put these weights in the matrix instead of the values of 1. So adjacency matrices are, well, they're good if we are dealing with smaller graphs, like, for example, the graphs representing molecules which have some limited number of nodes. However, such data structure has some limitation when we are dealing with large and sparse graphs. If we apply an adjacency matrix for a large and sparse graph, this can be spatially inefficient because we are still encoding the inexisting connections there. Furthermore, such representation is not permutationally invariant. So that means if we change the order of our nodes, we get a completely different matrix. There is a better data structure for big sparse graphs, and we call it adjacency list. Adjacency list is a list of tuples of the node indexes between we have existing edges. If we don't have an edge between two nodes, we just ignore that. So this data structure is spatially efficient, and it's also permutationally invariant. So it's a good way to encode sparse and large graphs. Also, before we proceed with graph neural networks, let's just revisit the basics of AI and deep learning. So on this image, I'm showing you a neural network, and it's an empty neural network. It can't do anything. In order to enable it to do anything, we need to train it. So we put this network through the process called training. And basically, the process of training means that we show to our network many examples. And this network extracts some patterns from this data. And it stores this pattern in itself in the form of the so-called weights. And for example, if we want to train a cat classifier, we will show thousands of cat images to our neural network, and the network will then have this new capability to recognize cats in the images. So in the output, we have this neural network with the weights, which has this new capability. Final state of using this neural network is called inference. We take our neural network, trained neural network, and we include it in our application. The process is called deployment. And then when we are using this application, we are showing some new data to our network, and we hope that it will predict us the values which we want it to predict. For example, if we show an images of some new cat to our network, we still expect it to tell us there is a cat in the image. So this is the deep learning training and inference process in the nutshell. Another important notion also to revisit is supervised and unsupervised learning. In supervised learning, we rely on inputs of an expert, or you, if you are training your network, you can be considered as an expert, in order to train the network. So in addition to a data set you have, you need to provide us, the network also with labels to the data set, so the ground truths. So if you, for example, are training a fruit classifier, you take a data set with pictures of different fruits, and you manually annotate, this is an apple, this is a banana, and the network learns from your annotations. A different category are unsupervised learning methods. So in unsupervised learning, we don't rely on expert input. So we just provide the network with a data set, and we let the network figure it out on its own. It applies analyzing and clustering in order to do that. And there is also something in between, which is called semi-supervised learning. In semi-supervised learning, you usually just label just a fraction of your data set, and on the rest of the data set, the network figures it out on its own based on this tiny labeled fraction. Graph neural networks are often deliberately designed as semi-supervised learning tasks. So let me now talk about examples of graph neural network applications and talk to you about different flavors of graph learning. So let's revisit our graph. We have nodes, we have edges. Also, our nodes have some node features, edges have edge features, and the whole graph can have global graph features. By using these features, we can use our graph as an input to our problem. And then our task here is basically to learn some function or neural network which will provide the mapping between this input to 3 different kinds of output. And the output can be the graph level prediction, node level prediction, and edge level prediction. So let's go through them one by one. So in the graph level tasks, what we can learn here, we can compare graph level tasks to image classification. In image classification, we use our images as input to predict, is there a cat or not a cat? Is there a dog or not a dog? So this is our graph level prediction. Well, in the graph level, we use a graph to do the same. And let's just go by example. One cool example of such graph level classification is, well, Google has done this experiment. They used a database of molecules, which they labeled based on smell. And they trained a network which was able to distinguish what is the smell of a new molecule. I don't know what's the application of this, but the idea is really cool. We can also have graph level regression. And for those of you who are new to AI, regression is a prediction of some new value, a new continuous value, like, for example, an object's weight or a person's height. And researchers at MIT have performed graph level regression in order to predict toxicity of molecules. And basically, this led them to a discovery of new antibiotica, halicin, which is effective against some resistant bacteria. So node level node level learning in graph neural networks, this can be compared to image segmentation. And image segmentation, our task is to predict distinctive values of each pixel in the image. When applied to graph, we do the same, but for each individual node in the graph. So the good example of node level classification is the problem called Zachary-Karate Club. And this problem is considered to be the hello world of graph neural networks. So the idea behind is in a small town, there is a karate club. And there are two informal leaders, Mr. Hai, the instructor, and John A., the administrator. A conflict arose between those two, which led to the club splitting in two halves. The first half, they stayed with the instructor, Mr. Hai. And the second half, they decided to change an instructor or just dropped karate. And the task here is by using a social network of the university to predict which half of the club stayed with Mr. Hai and which half went and searched for another instructor. There is a public data set available for that and many open source solutions on GitHub. So yeah, if you want to start with GNNs, it's a good starting point. It's a good toy example. You can also apply node level regression. And it's again, we are predicting continuous values, but on the node level. And one example of such a study, researchers at Cornell used geospatial and temporal information in order to predict yield of crops in the United States. Another type of tasks are edge-level tasks. And again, we can also have edge-level classification, edge-level regression, but also we can model the tasks of link prediction. And link prediction is very popular on the websites like e-commerce or digital media like Netflix, where we basically recommend to a user, we provide the user with new recommendations based on the content they consumed before. So if you're, for example, shopping online, then the shopping platform says, well, maybe these are the goods you want to buy. Also, this function is implemented in social networks. Like on Facebook, you all know that there is this feature, people you may know, very sneaky. So edge-level classification can be used to predict fraudulent transactions in banking. So in this case, we model our system as, we put merchants and credit card holders as the nodes of the graph. And we model the transactions as edges, and then we classify the edges, whether they're suspicious or not, right? A cool example of a graph regression, edge-level regression. So DeepMind has published this white paper where they describe how they do it on Google Maps. So they take the road segment and they divide it into some smaller segments, and they associate, like with each segment, they associate a new node. And then using node embeddings, they are able to predict the ETA, time to travel from A to B. They claim that since introducing that, the performance increased to 40% compared to the previous production baseline. So now to the most exciting part, how do we actually train graph neural networks? And in order to train something, we need to encode some certain features. And I already mentioned we have node features, edge features, and global features. So we need to take these input features and we need to transform them into some digestible format for the neural network. In the older days, feature engineering had to be applied, and we used the things like node centrality, eigenvector centrality, and so on in order to model this. These days, we are more relying on the artificial features called embeddings. And these features like embeddings, they are learned features. In order to learn that, we need to apply an algorithm called message passing. So let me show you how message passing works. So this is our input graph, and let's say we start from the node C. A cool thing about graphs, they are permutationally invariant, which means that we can start from whatever node we want, and the result will be the same. So let's say we choose to start from the node C. We have our node C. What we do now is that we collect the information from the neighbors B and D. We aggregate this information and we transform it by some sort of a neural network or some unit. and we update the value of C by the values collected from its neighbors. What's more, we continue and do that the same with the information from the neighbors. So we aggregate the information from the 2-hop neighborhood and also update the values of B and D. Furthermore, we can actually apply some neural networks in these nodes. It makes it more complicated, but also more efficient. And we perform this step n times, and this parameter n is something you decide on, so it's a hyperparameter. By doing it n times, you make sure that each node encodes the information from the node n hops away from it. So this is how we train our embeddings. And then we have this, and we stack it as layers. So let's look at stacking the layers. So this is our layer K with the embeddings. And we basically do the same process. We have our node C. We aggregate the information from the node C. We transform it by applying some neural network or some function. And we get the new layer K. And we can have the number of layers you decide on as an engineer. So this is how message passing works. The rest is simple. The rest is very similar to how you train convolutional neural networks. And again, we can have here activation and normalization layers. We need to estimate our loss function based on the task. And we perform the algorithms like gradient descent and backpropagation. I highly encourage you to look up these definitions from the introductory deep learning trainings. A tricky part here, though, that those of you who know how AI works, you know that we usually split our data set into training, validation, and testing. It is very important to do that in order to see that our network generalizes on the new data. So with the graphs, it's trickier because a graph itself, like one single graph, can be a data set on its own. So the way to approach this is by applying the so-called transductive split. We compute the embeddings on the whole graph, and then we randomly split our graph into training, testing, and validation nodes. And, well, then we deal accordingly with them. So now I covered all the basics you need to know in order to start training graph neural networks. And I have really good news for you. You don't have to implement this all from scratch. There are already really good frameworks available for them, and the most popular ones are the DGL framework, which is a deep learning framework agnostic. So DGL works with PyTorch, TensorFlow, and then also PyTorch and TensorFlow, they have their own implementation of graph neural networks. There is PyTorch Geometric, and TensorFlow has it also since recently as well. Furthermore, you can actually train graph neural networks on GPUs. And with this QR code, I'm sharing with you a video of my colleagues where they describe a platform for graph neural network training, which is free to use, and it is supplied by NVIDIA, this platform, and it works well on our GPUs. So check it out if you want to start training GNNs on GPUs. A further list of free resources. First of all, I encourage you to check our NVIDIA technical blog, where we constantly sharing insights from business, insights about software and hardware. The second link is the NGC. NGC is our software hub, software repository, and we share the software with you for free in the form of Docker containers. And the DGL container is also included there. We have our NVIDIA developer program, which, you can register there and you can benefit from being a member of the developer family. And finally, the last announcement, our GTC conference is coming again this September, virtual, so it's also full of brilliant talks about AI, highly recommended. With that, let me just wrap it up, my talk. So these are the key takeaways I want you to bring home. First of all, we've learned that you can model anything using graphs. And these graphs can have different structures and different properties. We have learned that you can represent graphs by adjacency matrix, But also, maybe for larger sparse graphs, it's better to use adjacency list. We've learned about flavors of geometric learning, and we've learned that we can have node level, graph level, and edge level predictions. We've learned that in order to train our graphs, we need embeddings. And embeddings, these are special features encoded in the graph, which we learned by the algorithm called message passing. And message passing consists of the three following steps: aggregate, transform, and update. Finally, we've learned that you don't need to spend hours on implementation work because there are already great frameworks available. With that, happy training.
Thank you very much. Thank you very much, Ekaterina. So you already talked a bit about the applications. So I would be interested, is there or are there any problems for where in specific software developers can like solve with GNS or where they can use it?
Yeah, this is very futuristic. Like, you mean something like generating new code, or theoretically this could be applied by graphs. It's still an active area of research, but it's definitely a very interesting topic.
Yeah. So we also have some questions from the audience. Is there a risk with data leakage during the transductive split from training the embeddings on the whole network?
That's a good question. And the thing is, you can actually control that by designing the value of the key hop neighborhood. And if you don't go that deep, you kind of make sure that not the whole graph gets reflected in your current node.
Okay. And can the technique used with semantical knowledge graphs as well?
Why not? I mean, if you can model it as a graph, you can train it. A semantical knowledge graph is a heterogeneous graph, and yes, you can apply neural network training on that.
Okay, so maybe a last question. Are learned graph embeddings comparable to word embeddings in first containing interesting information and second reusability?
Yes, so in language models we have this word to vec, and in graphs we have node to vec. This is very similar, and the idea is the same.
Okay, and there's a last question. You already said GNS is something very new, and there are a lot of application fields. So somebody asked, do you apply GNS in any problem in NVIDIA?
We have it as a research area, but as you know, we are a service provider, so we provide hardware and we provide software to enable you as developers with our tools. So we don't solve the problems, but we enable you with tools to solve these problems.
Okay, so thank you very much, Ekaterina.
Thank you.